All right, so what we're looking at today, if you look at our section title, it says we're solving special systems of linear equations. We're not going to learn another way to solve. So don't be like, oh, Miss Golly, I'm still trying to get things straight with the graphing, substitution, elimination. We're not learning another new way, okay? We're just looking at some special cases for what we've been solving for the last few weeks, okay? So our main objective right now is, as you look at your sheet, the whole top piece of it goes together. So if you fold your sheet in half horizontally, the whole top piece goes together. So the questions that are in that upper left-hand corner that you see on my screen now, it goes with this system. It goes with this system right here. So what we want to do is we want to start off by graphing. So I wanted to make sure that we saw a few different types with the graphing. Equations in standard form and equations in... All right, so our first equation that we're going to graph. And if you guys need to, remember, write the equations. Oops, sorry guys. Write the equations next to each other. I think when it comes to the graphing, too many of us look at the first equation and maybe get an x-intercept, and then we look at the second equation, we try to get a y-intercept, we graph one line, it's like, wait a minute. Last trimester when we did graphing, all of you could graph with standard form and all of you could graph in slope-intercept form without any help from me. But now we have two equations together, now it's like we get things all jumbled up. So here we go. Let's take a look at, I'm going to take a look at this equation. I have y by itself. If I have y by itself, which form do we have? Do we have slope-intercept or do we have standard? We have y equals mx plus b. That's our slope-intercept. That's our y equals mx plus b. So we have our m. And we have our b, which is our y-intercept. So if you have y by itself, that's our slope-intercept form. And I know for some of us, like, well, Miss Golly, I could do that because on the test you would have pick out slope, pick out intercept, and then graph. So you knew which one to use. Now we have to be able to pick them out. So if you have y all by itself, you've got your slope-intercept form. Y equals mx plus b. We start with the y-intercept. The y-intercept goes on the y-axis. That's our vertical one. So we go up 3, and we put a point. Now from there we use our slope. From there we use our slope. We like our slope to be a fraction. So I'm going to put -2 over 1. And we have a couple different options on how we can move with the negative slope. What's one of my options? How can I move? We could go up 2, but then over which way 1?
Right.
If I go up and right, am I negative?
Down.
Up and...
Mr. Albert, I need you to call the office, please. Extension 3000. Thank you.
So we have up 2, left 1. Or we can go down 2, but then which way do we have to go? And we've got to go right 1. Make sure when you're talking about slope, if it's negative, one of your directions has to be a negative direction. If you do 2 negatives, you're going to end up with a positive. So from our y-intercept of 3, we're going to go up 2 and left 1. And I'm going to keep that pattern going. I've seen a lot of you doing that when we've been graphing, and that's awesome to see. And I've been seeing a lot of you then also go the other way, go down 2 and right 1, because you know we're looking for the lines to intersect. So the more perfect I can make that first line, the more exact I can be, the better the chance I have that I get the correct intersection point. If I just put down 2 points and I draw a line, even though I use a straight edge, it might not actually be the straight line that we need. It'll look straight, but it might not be the line that we need. Whoops, just like that. Here we go. All right. So now for our second line. For our second line, let's go purple. For our second line, we've got x and y on the same side. X and y on the same side, that's our standard form. That's when we want to find our zeros, which would give us our intercepts. And it doesn't matter which one you put 0 in for first. Doesn't matter at all. For a lot of you out there, I know you're choosing to put 0 in for x first. Okay, fantastic. Let's do that. If I put 0 in for x, what happens to the x? It's gone, right? It's just a 0. Do I need to write the 0? I don't need to write the 0. Negative y equals 3. Now here's where some of us are getting stuck. Like, Miss Golly, I swear I graphed it right. I found the intercepts and my intersection point isn't checking out. At this point, have I solved for y? Is y by itself? What's still in front of it? Negative 1. How do I get rid of that negative 1? Divide by it, yep. So my y is really negative 3. So just be super careful when you have that negative in front of a variable. There's really a negative 1. A lot of you have been writing the negative 1 there, which I think helps a bunch. Now we have to do the same thing, except 0 is going to go in for y. When I put 0 in for y, subtracting 0, well, that's subtracting nothing, literally. My x is 3. Make sure when you're finding the intercepts, it's not just I take the number that's in front of x and I stick it in there. I have to actually put in the 0 for y, because on the entire x-axis, the y is 0. All right, so we have 0, negative 3, so the y is negative 3. There we go. And my x is positive 3. If you want to, and I saw a lot more of you doing this when you were practicing the graphing yesterday, I go up 1, 2, 3, and I go right 3. So I saw more people doing a few extra little points on their graph, just to make sure they had that nice straight line. So even though you're doing standard form and you're finding intercepts, you could still grab your slope from that pretty easily. We all rock slope triangles when we did our graphing unit. All right, so now some of you yesterday handed me in 9 graphs, beautifully graphed graphs, and I gave it back to you. I said, you haven't given me a single answer, though. How do I actually answer this? What's the solution?
You have to have to find the points of what the lines are.
Yeah, we need the point where the line intersects. We need that point, that actual ordered pair. What is that ordered pair?
2, negative 1.
2, negative 1. 2, negative 1. That's my actual ordered pair. So let's take a little look at that first sheet. It says solve the system by graphing. Check, we did. What did we get? 2, negative 1? So I'm in the upper left-hand corner of your sheet. It matches with what we just did. It says identify the slope for each equation. Well, the one that we graph standard form, we said we went up 3 and then we went right 3 to get some more points. So it would be 3 over 3. My slope was really 1. That was for the top equation. The bottom equation was in slope-intercept form, and the other one was negative 2. The big key here is when I graph them, I can see if the slopes are the same or if they're different. These two slopes are definitely different. They're not even close. 1 and negative 2. They are completely different. It says identify the y-intercept for each equation. As you look at your graph, I can't have both screens up here at once, so as you look at your graph, we have a y-intercept of 3 for one of the equations. oops, sorry, negative 3. And the other one is at positive 3. If you're like, wait, Miss Golly, where are you getting those? Look at your graph. What's the point where your line is on the y-axis? One of them is at negative 3, one's at positive 3. So those, once again, are different. How many intersection points did we have? How many places did the two lines meet? Just one. We just had one. So we solved by graphing. We found one intersection point of 2, negative 1. When we had that one intersection point, our slopes were different. And in this case, our y-intercepts were different. Now, step number 5 says solve the system algebraically. When you're asked to solve algebraically, that's our substitution or elimination. And I know some of you are like, Miss Golly, oh man, I really love elimination. Elimination is my favorite. It seems to be less work. Now, a lot of you liked elimination until you got to some of those last problems on your practice sheet, or the ones you did in your student journal last week, and you didn't like them so much when you had to rearrange things. So this system right here, is this system going to go so well with elimination? Is this system ready for me to eliminate? Because I know a lot of you loved elimination. No. X and Y, they're not on the same side in both equations. I'm going to have to do some moving to get them there. So instead of having to mess around with switching equations around, look at your second equation. We have a y all by itself. This system has a variable already solved for. This system is ready for substitution. And I know some of you are like, oh, Miss Golly, but elimination was less work. It wasn't always less work, guys. The only time elimination is less work is when you get that nice perfect system that says 2x and a negative 2x, and they're just going to eliminate for you. With this system, we'd have to rearrange the bottom equation. We'd have to do some multiplying, and then we can eliminate. So this one, it's going to take a lot more work up front to eliminate. So this one, substitution, it's ready to go. Y is by itself. Use substitution. The y is already by itself. So we circle it. We make our blob, if you will. It's y equals, so I've got to substitute in for y. It's y equals, so I have to substitute in for y. This system doesn't take any extra work for me to do substitution. So there's no little places where I can make little mistakes before I even start solving. So if you come across a system and you already have a y equals or an x equals, substitution is going to be less work for you. So what that looks like, oops, sorry guys, we've got x minus negative 2x plus 3, and we equal 3. Make sure you're using parentheses. I've seen more and more of you, as you've been doing your practice, you've been sneaking that negative 1 in front of that y. And for some of you, that has helped a lot. It has helped a lot when it comes to distributing. It helps a lot when it comes to substituting in. It's been looking really good. Because now when I distribute to solve this, for some of you out there, your frustration with substitution was not the actual concept of substituting. You guys have got that. You know how to take what y equals and put it in for y. We just kept making some little mistakes when we solved, and that happens. So don't think substitution is, oh man, that's the harder way to go, it's more work. We just have to maybe sometimes slow down when we solve our equations. Combine our like terms. We've reviewed this the last few days. If they're on the same side of the equation, I do not change any signs. The only time I want to do the opposite thing is when I want to move the x to the other side, or the 2x to the other side. So I have a 1x and a 2x, I get a 3x. Add our 3. 3x equals 6. And we got x equals 2. which matches our graph. One of the reasons I like substitution best is because when I go to find my other variable, I just have to go back to my circled equation. I just have to go back to the blob, and I'm going to be set. Y equals -2 times my x is 2 plus 3. Y equals -4 plus 3. My y equals -1. So we graphed and got 2, -1. We did substitution, we got 2, -1. Those things should agree. It doesn't matter what method you use to solve. You'll get the same solution. You'll get the same solution. So if we look at our step number 5, it says solve. How many solutions are there? I know we solved and found an x and a y, but that's one solution. It's that ordered pair, just like we got when we graphed. One solution. One solution. The first type that we saw, that's what we've been solving. So like, Miss Guy, what's so special? You said the title was Special Systems. Well, okay, so let's take a look at our second one. Down in the bottom right-hand corner of your sheet, there's another system. As we look at both equations, I'm going to do what I did before. I'm going to take that top equation and I'm going to write it off to the side. Now, yeah, that takes a little bit more effort on your part to do that. But if I write them side by side, now I can really focus on them one at a time. So I'm going to focus on this left equation first. And I want to graph first. X and y are on the same side. X and y on the same side, that's our standard form. When we have our standard form, we should be thinking about x and y intercepts when we have our standard form. It doesn't matter which one you put the 0 in for first. I know for some of you, when we did our graphing unit, some of you just covered up whichever one you put the 0 in for. Some of you didn't write out a single thing and you could find intercepts perfectly fine. So it's kind of up to you how much work you need to show to find your intercepts. Doesn't matter what you start off putting in 0 for first. And actually, I'll go ahead, I'll put 0 in for x first. That's what a lot of you choose to do. So if I put a 0 in for x, that x term, it's just out of there. If you don't want to take the effort to have to actually put the 2 times 0, don't. Jump right to -y equals 6. That's fine. To get the y by itself, I need to divide by -2. So finding intercepts, remember, I don't just grab the number in front of the y and say, oh, -2 is my y-intercept. That'd be pretty sweet if it were that easy. Next up, we put a 0 in for our y. And again, if you want to put the 0 in, you can. If you just want to say, hey, if I put a 0 in for y, that term's out of there, up to you. 2x equals 6. We have to divide by 2 to get that 2 out of there. And our x is 3. So we have 0, -3, so -3 on the y. And 3 is 0, we have 3 on the x. Now if you wanted to, we can find more points. I'm going to start at the bottom point on the y-axis. I rise, I go up 1, 2, 3, and then I run to the right 1, 2, 3. So I can go up 1, 2, 3, right 1, 2, 3. 1, 2, 3, 1, 2, 3. Kind of sounds like we're counting for dancing. 1, 2, 3, 1, 2, 3. We can go the other way. And then we have our first line. Draw it as straight as I can up here. Can't use a straight edge on this screen, unfortunately. Now we know, just kind of the activity we're doing, I'm going to ask you for the slope. So we just talked about the slope of this line. We went up 3 and we went right 3. We had 3 over 3 or a slope of 1. And I just found that using our slope triangles, we did that a whole bunch when we were graphing. So we did that a whole bunch graphing. We can do a little slope triangle. Totally fine. What I want you to do is take a minute, the second equation, our negative x plus y equals negative 3. Take a minute, find your intercept, see where you would graph that line. X and y are on the same side of the equation. So that's going to be our standard form. When we have standard form, we want to use our intercepts to graph. I don't want to have to try to mess around with let's change things to get y by itself. That's where all those little mistakes happen. We make a mistake adding, we make a mistake dividing. Let's just use 0. 0 is such an easy number to work with. Put 0 in for, I know a lot of you like to choose x first, that's fine. If I put a 0 in for x, negative 0, well, that's just 0. I'm left with y equals negative 3. Then what we have is put a 0 in for the y. So I get negative x plus 0 equals negative 3. So negative x equals negative 3. We know there's a negative 1 really in front of there. So we divide by it, just like we did in our last example. And my x equals 3. What's going to happen when I graph this line? Let me grab a different color here. Y is negative 3. There's where y is negative 3. I just colored it red. Here's where x is positive 3. I just colored it red. Look at our x and y intercepts. I highlighted them in red on the graph. I just put boxes around them. What do you notice about them? They're the exact same thing. So whether I look at the little T-charts we made or whether I look at the actual graph, they're the exact same. They're the exact same line. I can't quite draw it straight enough up here, but they're the exact same line. So if we take a look at our questions, it says identify the slope. We identified the slope in the first one. We had up 3, right 3. So the slope in the first one was 1. We don't have to do it for the second one because we found out it's the same line. So the slope for the second one's also 1. They're the same slope. The y-intercept, if you check your graph or you check the little T-charts we made, either way, the y-intercept for equation 1 was 0, negative 3. For equation 2, it's 0, negative 3. The y-intercepts are the same. Same slope, same y-intercept. We have the same line when we graphed it. So here's the tricky part. How many intersection points are there? And here's what we have to stop and think about. These two lines are not floating on top of each other. So it's not the first line we graphed and then the second one's floating on top of it. The second line is right on that first line, matching it point for point for point for point. They are the exact same line. So they intersect at every possible ordered pair. The lines that we draw are made up of an infinite amount of ordered pairs. Not just the few that we plot. That whole line is nothing but ordered pairs. They don't work out perfect like 0, negative 3, but that whole line is nothing but ordered pairs. So how many intersection points are there? There's infinitely many. There's infinitely many intersection points. So if there's infinitely many intersection points, what does that mean for our solutions? If there's infinitely many intersection points, there's infinitely many solutions. Here's where the special system piece kicks in. If you have the same line twice, those two lines do nothing but intersect. There's an infinite amount of points that make up a line, so those two lines intersect infinitely many times. We don't know how many, because those lines keep going forever and ever and ever. It's why there's the arrows on the ends. Our last task with this one is to solve algebraically. It says substitution or elimination. I have negative x plus y equals negative 3. 2x minus 2y equals 6. Now for this one, if you like elimination, this one is set up for elimination. We've got x and y on the same side for both equations. And as I look at my equations, I really have a negative 1 in front of my x, and I have a 1 in front of my y. I could multiply that top equation by what? And I could get rid of my x's. What can I multiply the top equation by? And we'll say c to the x's. Multiply by. If I multiply by 2, my top equation becomes negative 2x plus 2y equals negative 6. Remember, with elimination, we're looking for that pair of opposites, like positive 2, negative 2. If we don't have that, we can use multiplication to create it. So for this one, elimination was a pretty easy choice. I've got x and y on the same side, both equations, it's lined up, and I only have to multiply one equation to get my opposites. I don't have to try to multiply 2. So when I add these together, 2 plus negative 2, I get a 0 for my x's. But now I look at my y's. Negative 2 plus 2. Oh, well, that's a 0 also. That left side, I just have a 0 on it. X and y were both eliminated. That's new for us. Then on the right-hand side, I have 6 plus negative 6. No matter how hard I try, that's nothing but a 0 either. Our very first unit of the year, we solved equations. And we had some equations that came out just like this. 0 equals 0. 0 equals 0. That's always true. That's always true. It's not going to matter. It's not going to matter which ordered pair I pick. So any ordered pair on this line, no matter what one I pick, it's going to make both equations true. So when we had that, when we were solving equations, when something like this happened, it wasn't a no solution. It was an infinitely many solutions. 0 equals 0, that's always true. So I have an infinite amount of possibilities that I could substitute in for x and y. Any ordered pair on that line, and it keeps going on forever and ever. That's what the arrows mean on the end. So when we solved, just going to pop back here real quick, solved the system, we chose elimination. X and y were on the same side. I only had to multiply one equation to get my opposites. How many solutions? We had infinitely many. We had infinitely many solutions. We got the same line right on top of itself. Or the two equations are the exact same. They looked a little different to start, but once we multiplied by 2, everything eliminated. We had the same equation twice. Now, I know you might be thinking, oh, Miss Guys, there's going to be a whole bunch of these special systems to worry about. Nope, there's just one more type. There's just one more type. Flip your sheet over. There's just one more type. One more type. Flip your sheet over. And what I want to do is give you a chance to graph those two. Oops. All right, so if you have your two lines graphed, a lot of you have both graphed, I want you to make your pick. I want you to make your pick. Would you solve this with substitution or elimination? And then go ahead and try it. So you make your pick. Which would you choose? So this is me not telling you, here's what you have to do. I know a lot of our practice sheets, it was practice graphing. Then it was practice substitution. Then it was practice elimination. Now you've done a lot of the practice. If you've done the practice, then you should be ready to rock and say, yep, Miss Golly, I know which one's easiest on this. I know what makes sense on this. So try it out. Take your pick. Take your pick. If you try one method, you're like, ooh, this is not working out, try the other. Substitution or elimination, your choice. See what you can do. So again, you have your choice. But I also know some of you are just sitting there waiting for me to start. You get your choice. I know some of you are like, oh, Miss Golly, oh man, that elimination seems like a lot less work. If I look at this system though, my X's and Y's, they're not lined up. They're not all on the same side. And I've got a fraction sitting there. I don't know if I want to try to figure out what I'm going to have to multiply by to maybe make a fraction eliminate. As I look at this system, I see a y all by itself. I see a y that's solved for. When I look at this system, x's and y's aren't lined up. So when I look at this system, elimination is not going to be my choice. My x's and y's aren't lined up. I've got a y solved for. I have a y all by itself. This system, the way it is set up, we should be substituting. Could you do elimination? Could you move the 1/2 x over and then multiply to try to eliminate? Yes, you absolutely could. But I'm all about trying to help you guys find the easier choice with these. I can't make these problems less work. So once we choose substitution, I can't make the steps any less. Or once you choose elimination, I can't make it any less steps than what it is. That I can't do. But what I can do is try to help you see what the easier choice is going to be. The one that will be less work for you. With this one, I don't have to rearrange anything, and I can do substitution. So when I do that, don't let the fraction scare you. We have x plus 2, and instead of y, I have negative 1/2 x minus 3, then that whole thing equals 8. Then that whole deal equals 8. Distribute, and actually this works out rather nice. 2 times negative 1/2 just gets me negative 1. 2 times negative 3, negative 6. I have a positive 1x and a negative 1x. They're on the same side. I don't do anything opposite at all. When they're on the same side, I leave them alone and I just combine them. So no matter how hard I try, 1 plus negative 1, it's going to be 0. No matter how hard I try, that x is gone. And I'm left with negative 6 equals 8. All my variables are gone. Now I know you might be thinking, oh, Miss Golly, so it's just like the last one we did. It's similar to the last one we did, because in the last one all our variables eliminated too. But on the last one after we eliminated, we were left with something that was always true. On this one, after everything's eliminated, negative 6 doesn't equal negative 8. There's no solution. And we can also see this from our graph because there's no intersection. There's no intersection on our graph. There's no intersection. So that's a big old no solution. So if you solve it graphically, your lines don't intersect, your lines are parallel. If lines don't intersect, we can't have a solution. We're looking for the intersection point. If we solve it algebraically, substitution or elimination would have gotten us the same thing. We're left with two numbers that do not equal each other at all. Can't work. So if we were to look at this, because there's some of those early signs that can help you tell sooner, if we identify the slope for each equation, both of our slopes ended up being negative 1/2. Both of our slopes were the same. But now the y-intercepts though, the y-intercepts were different. One y-intercept was at negative 3, and the other y-intercept was at 4. So if you're looking at two equations, you're going to graph them, and you see they have the same slope, but they have a different y-intercept, we're going to have parallel lines. So how many intersection points are there? There's none. When we solved the system algebraically, we chose substitution because y was already by itself. How many solutions are there? There are no solutions. There are no solutions. So those are our three different types of systems. We didn't learn any new methods of solving. So it's not like, holy cow, Miss Golly, there's a whole new way to graph, or there's a whole new way to solve. No, we graph the same as we have been. We've done elimination the same as we have been, and we've done substitution the same as we have been. The only new piece for us is now there's that possibility that we get infinitely many solutions, or we get no solution at all. So just to sum up, this is in the bottom left-hand corner of your sheet. There's just a little summary table. I put little names at the top. I'm not going to hold you accountable for those names. I just want to be able to distinguish between them is all. If you have what's called an independent system, that's the first one that we had. That was the first one that we had. I'm just bringing everything together that we did today. And we had, and I'm just sketching this, we had an intersection at 2, -1. We had an intersection at 2, -1. We had different slopes. The y-intercepts we had, they were different, but they could also be the same. You could have different or same y-intercepts. That wouldn't matter. You have one intersection point. Whoops. You have one solution. And for this one, for example, it was 2, -1. That's the type of system that we have been solving. We would graph it, and we got one intersection point. To get one intersection point, you have different slopes. The y-intercept doesn't really matter. Could be the same, could be different. You've got one intersection point, one solution. That's the type we're used to. Our two new ones, and they call them special ones. We don't solve them any differently. We don't solve them any differently. When we graph them, this one again, I'm just sketching the graph. We got the same line. Same line twice. So that was different for us. We didn't do anything different to graph that line. We still just found our x and y intercepts, or use slope-intercept form if we needed to. We had same slopes, same y-intercepts. We had infinite intersection points. So we had infinitely many solutions. When we solved it algebraically, we got something like 0 = 0. You could also get, I just want to show you, you could get something like -6 = -6. You could also have the situation, depending upon the method you use to solve, you could just end up with x = x, or y = y. If you solve with substitution or elimination, and when it comes down to it, you have the same thing on the left side as you do on the right side, whether it's 0 = 0, 1 = 1, y = y, x = x, you're going to have infinitely many solutions. The last type we just saw. The last type we just saw, it's called an inconsistent system, but again, I'm not going to test you on the names of them by any stretch. The last type of system, we had parallel lines. To get parallel lines, your slopes were the same. Y-intercepts had to be different. Different y-intercepts. Whoa. Different y-intercepts. No intersection. So no solution. When we solved algebraically, we've got something like 6, negative 6 doesn't equal 8. You could get things like 1 doesn't equal 7. Negative 5 does not equal negative 3. So it's not always going to be negative 6 doesn't equal negative 8, and that's what I need every time. You're just going to be left with two values that don't equal each other at all. And that's what you will be left with.